Hello all. So in last lecture we saw that when we grow the decision tree to the maximum depth without any constraint, then we get some really I'll show you that we can't interpret that decision tree, and we'll get some decision tree like this which we can't even interpret. Yeah. So this is clearly an overfitted model of our decision tree. So the question is, why I'm saying overfitted model here, that why it's not underfitting and just overfitting. So we'll try to see this question, that why growing to the maximum depth leads to overfitting. So first of all, let me start with the very basics, that decision tree makes very few assumptions about the training data. So it's like, if I'll compare with linear regression, so compare with linear regression, then it assumes that our data should be linear. Let me write it whole, that data should be linear. But here in decision tree there is no assumption. It won't check like whether the data is linear, whether it is in some scale or not, because this is the advantage, or you can say the beauty of decision tree, that we can see everything first of all, that what is happening inside the algorithm, and that's why it is called white box. This I am saying many times in my lecture series. And the other thing is that we don't have to assume anything about data. We don't even need to scale it. Like, in order to have the proper scale, we can just use our given data set as it is. So it doesn't make any assumption, unlike other algorithms which can assume that the data should be linear and so on and so forth. The second point, which is very important, is that, so if my decision tree, so if a decision tree is left unconstrained, so if we will not regularize it, then what will happen is that the, the structure of the decision tree, so decision tree structure will adapt to the entire training data, isn't it? Because we are not even concerned about anything about linearity of the data or anything, even scale, nothing. So it's not like, it is even not prone to the it will be prone to the outliers, because we are not even doing anything with the data. We are just as it is giving to the decision tree algorithm, and we are building it. So there are chances that if there is an outlier, then our decision tree will adapt to this outlier and it will grow accordingly. So if, let me just give an example side by side, that if I am growing my decision tree like this, so if there is some outlier, let's say this is a leaf node at the end, this is a leaf node. So, and if there is this leaf node that we are getting, if this is because of the outlier, then we can't do anything, because our tree will adapt to that outlier as well, because it will grow because of that outlier, even though we know that this is outlier and this node is not needed here, but it will grow, right? So in short, I can say is that if it is left unconstrained, then decision tree will adapt to the entire training data. Let me write the training data. And so, and obviously it will try to fit it closely, the entire training data, and this leads nothing but overfitting, because we don't need fitting to the outliers, because this is the outlier, right? And we don't need this fitting, but decision tree will do that. And that's why growing it to the maximum depth will cause overfitting. I hope this answers this question correctly. And because of that, what we have to do, we have to regularize the decision tree. So in machine learning terms, we will call something called as regularization, that we are also doing in linear regression and in any machine learning problem, in order to reduce this overfitting, right? Also, maximum depth, like more is the depth, more are the chances of overfitting. But if there is less depth, then there are chance of underfitting as well, right? So we need to be optimum, and we will see that we'll be using the grid search algorithm in order to find the best optimum parameters. In the very next lecture you will see that. So that's why the decision tree is sometimes often called as a non-parametric model. So such a model in which there is no constraint, nothing, it is called a non-parametric model. But we will see there will be many constraints, like maximum depth we can pass as an argument in our scikit-learn decision tree classifier that we have. So we'll see all this thing in the very next lecture. And so such a model is called non-parametric model, but not because it does not have any parameters. This is called non-parametric. This is important, that This is called a non-parametric model, but not because of this is because, okay, but not because, like, it does not have, let me remove it, it does not have any number of parameters or any parameters. But why it is called non-parametric model? Because the number of parameters is not determined. So let me write in the fresh page, but why it is called non-parametric? Because but the number of parameters are not determined prior to the training. So before training, we can't determine anything. We'll just go with the flow. I can say like that. So prior to the training. So the model structure is free to stick to any of the training data set or the outlier that I showed you in the last slide. So it will stick to our entire training data set and it will grow accordingly, and that's why the maximum depth is causing the uh, chances of, or we can say the risk of overfitting. And apart from that, what I can say is that in parametric model, that is linear regression, I'm just comparing these two things, that in case of parametric models, so what was happening in case of parametric models like linear regression, that we have a number of parameters defined, so has a predetermined parameters. So what we can say is that its degrees of freedoms are limited. It's not totally free like a decision tree to grow at any number of depth or at any depth. So degrees of freedom are limited. But in decision tree, it's not at all limited. You can grow tree to the maximum depth. No one cares. Yeah? And thus reducing the risk of overfitting. So in this, degrees of freedom are limited. So less will be the overfitting. But we can also say that there is an increasing the risk of underfitting, because this is always a trade-off. So when we limit our degrees of freedom, there are chances of underfitting. So let me write it. It is underfitting. So the conclusion is that we should not be overfitting or underfitting. We should be having something optimum. Yeah, and that is what we'll do in decision tree. We'll see maximum split or minimum number of samples that are needed. All this thing in a very detail with code in the next lecture. So I hope I answered this question and this video is informative. We'll see each other in the very next video. Thank you.